Partial fractions. Let's begin with the question, what are partial fractions? So to write a sum or a difference of fractional expressions as a single fraction, we bring them to a common denominator. So for example, if I want to add these two fractions together, I have to multiply the denominator and the numerator of each fraction by the factor that it's missing to make a common denominator. So this fraction here needs the factor 2x plus 1, and this one needs the factor x minus 1. After multiplying the numerator and denominator by these factors, we then add these fractions together and we come up with the result. Now the question is, if I had given you this and asked you what fractions do you add to get that fraction, this would now be the answer. So a partial fraction, or the process of decomposing something into partial fractions, is the process of determining what fractions would I have to add to get a certain fraction. Now, as we begin to answer this question, we have to consider 4 different cases. The first case is when the denominator is a product of distinct linear factors. So when you factor your denominator q of x, each of the factors that it factors into is a different linear factor. And one thing I need to say before we begin this process is that we are under the assumption that the original fraction you have is a proper fraction. So the degree of the numerator must be less than the degree of the denominator. So in our first example here, notice the degree of the numerator is 1 and the degree of the denominator is 3. So this is a proper fraction. The first thing we need to do to find the partial fraction decomposition is we have to factor the denominator. So we have x cubed plus 2x squared minus x minus 2. Now you can use synthetic division to factor this, or in this case, we can just factor this by grouping. So if I pull out an x squared out of the first 2, and then I pull out a negative 1 out of the second 2, you can see that we have a common factor of x plus 2, and that's going to leave us with x squared minus 1 left over. And then, of course, x squared minus 1 can be further factored into x minus 1 times x plus 1. So the original fraction, 5x plus 7 over this denominator, can now be expressed as 5x plus 7 over x plus 2 times x minus 1 times x plus 1. And now the decomposition process, according to the guidelines on the previous page, we can break this down into the sum of, in this case, 3 fractions with some unknown constant term on top and each of the factors in the denominator. So what that means here is that we're going to have a fraction with x plus 2 in the denominator, and then a fraction with x minus 1 in the denominator, and finally a fraction with x plus 1 in the denominator. And the numerators are going to all be unknown constants, which I choose to call a, b, and c. So now the next step is we're going to multiply both sides by the least common denominator, and that means we need to multiply by all 3 of these factors here on both sides. And on the right-hand side, we have to be sure to distribute that to all 3 terms. So on the left-hand side, these simply cancel out, and that is going to leave us with 5x plus 7. On the other side, we have to distribute here. And when you do that, the x plus 2 cancels out the x plus 2, and we get a times x minus 1 times x plus 1. When we multiply to the next term, the x minus 1 will cancel out, and that is going to give us b times x plus 2 times x plus 1. And finally, multiplying to the last term here, x plus 1 cancels out, and that will give us c times x plus 2 times x minus 1. And in the case where all the factors are distinct, there's a little bit of a trick in terms of what you can do to solve for a, b, and c. So what I'm going to do is I'm going to let x be equal to negative 2. Now, why did I choose negative 2? I chose it because I can see that if I plug negative 2 into here, this becomes 0, which means this whole term becomes 0. Likewise, when I plug in negative 2 here, this whole term will become 0. So when I plug in negative 2, I really only need to plug it in here and here. And so doing that is going to give us 5 times negative 2 plus 7 is equal to a times negative 2 minus 1 times negative 2 plus 1. And this is going to be negative 10 plus 7, which is negative 3, equals a times negative 3 times negative 1. And this is negative 3 equals 3a, which means a is equal to negative 1. And now I do the same thing for the other factors. So I can see that if I let x equal positive 1, that will make this go away, right? Because 1 minus 1 is 0. And if I let x equal positive 1 here, this will go away. So I'm going to let x equal 1 everywhere we see an x. So that's going to be 5 times 1 plus 7 is equal to. I don't really need to show the work here because I know when I plug in 1, I get 0. So I just really need to plug in the 1 here, and that's going to be b times 1 plus 2 times 1 plus 1. And of course, when you plug in 1 over here, this cancels out. Doing the math here, we have 12 is equal to 6b, right? We have 3 times 2, which is 6. And of course, this means that b is equal to 2. And finally, I can let x be equal to negative 1. When we plug in negative 1, we're going to have 5 times negative 1 plus 7. And the reason I chose negative 1 is because when you plug in negative 1 here, this cancels out. When you plug in negative 1 here, this cancels out. So we only really need to plug negative 1 in over there, which gives us c times negative 1 plus 2 times negative 1 minus 1. And this is going to be 2 is equal to negative 2c, which means that c is equal to negative 1. And so now finally we take these three numbers, a, b, and c, which we now know are these numbers here, and we're just going to plug those in, and that gives us our partial fraction decomposition. And so the original fraction we had in the beginning, right, this fraction right here, is equal to the sum of these three fractions. Now, in the second case, it is possible that some of your linear factors could be repeated. In the event that they are repeated, you need to make sure that you have a representation for each of those repeated factors up to the power of the repetition. Let's take a look at an example. So in this next one here, first of all, let's just notice that the degree of the numerator is 2. The degree of the denominator, you have a third degree multiplied by a first degree, so that's a fourth degree. So this is definitely a proper fraction. And it's already factored for you, which is very nice. So we have x squared plus 1 over x times x minus 1 to the third power. All right, so there are two linear factors. There's x and there's x minus 1. But x minus 1 is raised to the third power, so it is a repeated linear factor. So what I'm going to do is I'm going to have a denominator for each power of the repeated linear factor up to the power that we have. And what that means, since this is a third degree, I need to have x minus 1 to the first power, x minus 1 to the second power, and to x minus 1 to the third power. And then, of course, x is a single factor because this is a first degree there, and so I only need one of those. And then, of course, we're going to have a, b, c, and d. So this is the setup. Now, in terms of solving for a, b, c, and d, I'm going to take the same approach. We're going to multiply both sides by the least common denominator. And then, of course, we get cancellation on the left-hand side. And on the right-hand side, we have to multiply this to all four of these. And each time we multiply, we're going to get some cancellation. And when you multiply and cancel carefully, oh, and by the way, this was x minus 1. I put x plus 1. Let me fix that real quick. I'm talking about right here. There we go. I hope that doesn't bother anybody too much. Did the math correctly here. All right, so from here, what I'm going to do is just let x be equal to a couple of numbers. One number I definitely want to let x be equal to is 0, because when I plug in x equals 0 here, here, and here, all of these go away. When I plug in 0 here, we get 0 minus 1 to the third, which is negative 1, times a. And when I plug in 0 here, we get 1. So we get 1 equals negative a, which means a, of course, is negative 1. Then I'm going to let x equal 1, because when we plug 1 into here, and here, all of these are going to cancel out. And we get 1 squared plus 1, which is 2. And on the other side, when we plug in 1 here, we get d times 1, which is d. And that's done. So d we know is equal to 2. But notice that there are no other values of x that we can plug in that's going to cancel any factors. And that's because there were only 2 distinct linear factors, right? So what I can do now is I can just let x be equal to any other number. So the simplest number I can choose would be x equals 2. Plugging in 2 here is going to give us 2 squared plus 1, which is 5. Now, if I plug in 2 on the other side, keep in mind that we know the value of a and we know the value of d. So a is negative 1. And when I plug in 2 here, I'll go ahead and write it down. We get 2 minus 1 to the third power. Then we have b times 2 minus 1 to the second power. And I put b because we don't know what b is. Then plus c times 2 minus 1. And then finally, d we know is 2, and then x is also 2. So now we simplify, we get 5 is equal to, this is 1 times negative 1, which is negative 1. Then we have 1 times 2 times b, which is 2b, so positive 2b. 1 times 2 times c is positive 2c. And finally, plus 4. Simplifying a little bit more, we're going to have negative 1 plus 4 is 3. Subtracting 3 from both sides, we get 2 is equal to 2b plus 2c. And then dividing by 2, we get b plus c is equal to 1. Okay, now we're going to save that. And we're going to plug in one more value of x. And I think the other simple value of x that I can plug in would be x equals negative 1. Putting negative 1 into here, we're going to get 2. When we put negative 1 in here, we get negative 2 to the third, which is negative 8 times a. So that's going to be negative 8 times negative 1. Then, letting x equal negative 1 here gives us negative 2 squared, which is 4, times negative 1 is negative 4 times b, so minus 4b. Plugging negative 1 in here gives us negative 2 times negative 1, which is 2 times c, so that's positive 2c. And finally, plugging negative 1 in here, and then keep in mind that d we already know is 2, gives us 2 times negative 1, which is negative 2. So if we do the math here, we have positive 8 minus 2 is 6. Subtracting 6 from both sides will give us negative 4 equals negative 4b plus 2c. Dividing by 2 gives us negative 2b plus c is equal to negative 2. Now I'm just going to take these two equations and solve for b and c. And you can do this a number of different ways. You could use elimination, you could use substitution. I think I'm just going to substitute. We know that c is equal to 1 minus b, and then I'm just going to plug 1 minus b right there. So we have negative 2b plus 1 minus b equals negative 2, so negative 3b equals negative 3. So b is equal to 1. And if b is 1, 1 minus 1 is 0, so c must be 0. So now we have a, b, c, and d. So I'm just going to come back to where we did our original decomposition, which is right here. And I'm going to plug in those values. So we have a over x plus b, which is 1, over x minus 1, plus c, which is 0. So if c is 0, this whole term is gone. And then finally plus d, which is 2 over x minus 1 cubed. And this is the partial fraction decomposition. Now, in the case where you have an irreducible quadratic, it's a little bit different in terms of how we set it up. So if one of your factors is an irreducible quadratic, you're going to take that factor, but on top you're going to have an ax plus b, rather than just having a simple constant. Now, what is an irreducible quadratic? You have to be very careful here. So for example, if I give you x squared minus 9, we know that this is not an irreducible quadratic because it factors into two linear factors. So we're not talking about this, but we're also not talking about this. Okay, x squared minus 5, you might say, is not factorable, but actually we can factor it if we just allow ourselves to use radical 5 as factors, right? So you have x minus radical 5 and x plus radical 5. So when we say an irreducible quadratic, we're talking about things like x squared plus 4, where the only way you can factor it is if you use complex numbers, okay? So an irreducible quadratic is something like this. So for example here, once again, notice that we have a proper fraction, and the denominator, if we go ahead and factor that, is going to be x times x squared plus 4. So the denominator is a linear factor multiplied by an irreducible quadratic factor. So when we go to break this down with our partial fractions here, one denominator is going to have x, the other denominator has x squared plus 4. In this numerator, we just need a constant, so I'll use the letter a. But in this numerator, we can't just put b. Okay, this is not correct. And the reason is because if you have a quadratic factor, on top you could have a linear factor, right? Because it just has to be proper. So anytime you have an irreducible quadratic, we have to have a linear factor on top. And in this case, I'm going to call it bx plus c. Now from here, it works the same way. So to solve this, we're going to multiply both sides by x and x squared plus 4. And then we're going to distribute that to both terms on the right-hand side. So on the left-hand side, these cancel out. On the right-hand side, we're going to have a times x squared plus 4 plus bx plus c times x. Now, to solve for a, b, and c, there's multiple different ways that you can do this. You can still let x equal 0, and that would get rid of this, and that would allow you to solve for a. So I do think that that is a good thing to do. So anytime you have a linear factor, go ahead and let x be equal to whatever makes that linear factor 0. So if I plug in 0 on the left-hand side, we're going to get 4. And if I plug in 0 right here, we're going to get 4 times a, so that's 4a. And of course, plugging in 0 here gives us 0. So we know a equals 1. Okay, so that's good. Now, how are we going to solve for b and c? There's a couple of different ways to do it. What I like to do is just multiply out everything on the right-hand side. So we're going to have, by the way, we know a is 1, so I can go ahead and plug that in there. So I have x squared plus 4 plus bx squared plus cx, right? So I'm just multiplying this out here. Now I'm going to group like terms together. So I've got 1x squared here plus bx squared. And that's going to be b plus 1 times x squared. And then we have c times x, and then we have 4. And on the other side, we have 2x squared minus 1x plus 4. And the only way these can be the same is if the coefficient of x squared equals the coefficient of x squared, the coefficient of x equals the coefficient of x, and of course the constant term must be equal to the constant term, and you can see that they are. So I know that b plus 1 must be 2, right? This must be equal to this. So that means b is 1. And I also know that c has to equal -1. And that's it. I now have a, b, and c, and now I can just come back up here and I can plug those in. So the partial fraction decomposition is going to be 1 over x plus, and then b is 1, c is -1, so we have 1x minus 1, so x minus 1 over x squared plus 4. And this is the partial fraction decomposition. And finally, if you have repeated irreducible quadratic factors, we treat those the exact same way that we treat repeated linear factors. So let's go ahead and take a look at an example. So in this case, let's point out first of all that we do indeed have a proper fraction here, because the degree of the denominator, you have a third degree times a second degree, which is a fifth degree. And then this right here is a sixth degree. So the denominator is an 11th degree polynomial. And on top you have a fifth degree. Now let's identify what we have. We have a repeated linear factor. We have an irreducible quadratic, and then here we have a repeated irreducible quadratic. So when I go to break this down, your repeated linear factor, x cubed, is represented by x, x squared, and x cubed. Then your irreducible quadratic, the first one, x squared plus x plus 1, just needs a single representative. And then your second irreducible quadratic, which is power 3, you're going to have 3 fractions to represent that one. So we have x squared plus 2, x squared plus 2 squared, and x squared plus 2 cubed. Now when you set it up, on top here we're going to have a, b, and c. And then we're going to have dx plus e here. And the reason I chose D is because D comes after C. And then each of these is an irreducible quadratic, so all of these numerators have to look like this. And so if we continue here, we're going to have fx plus g, hx plus I, jx plus k. And in this case, we're not actually going to solve for all these letters. This would take a very long time to do. We're more just interested in the setup of the partial fraction decomposition. And finally, what do we do if our original fraction is not proper? So notice the degree of the numerator here is 4. The degree of the denominator is 3. So this is not a proper fraction. So in this case, you have to use long division first. So we're going to have to take the denominator, which is this thing here, and divide it into the numerator. And so we have to go through this process. Now, we've talked about long division before, so I'm not going to explain every step here, but x cubed goes into 2x to the fourth, 2x times. 2x times x cubed is 2x to the fourth. 2x times 2x squared is 4x cubed. 2x times negative x is negative 2x squared. 2x times negative 2 is negative 4x. And then we have to change all the signs. Now this is kind of nice. These cancel, and these cancel. So we end up with just 5x plus 7. And we're actually done because 5x plus 7, this is a degree 1, and that's less than degree 3. So our original fraction can be written as 2x plus 5x plus 7 over x cubed plus 2x squared minus x minus 2. Now, if you recall, this is the first problem that we did in this section. So we already know the partial fraction decomposition for this, but basically you would just proceed from here and you would start decomposing this fraction. So in this case, our answer is going to be 2x plus the decomposition for this, which we already did in example 1. And that gives us this, And then the only thing that I would do here is, since we're adding a negative there, I would just change this to a negative sign. And so here is the complete partial fraction decomposition for this one. And that concludes this video lesson.